Okay, good morning. So today I'm finally going to get to the Z2 topological insulator. So I realized I went kind of slow. I hope that was okay. You know, I opted for going slow and doing a lot of things in detail rather than trying to cover lots and lots of material. But so today I want to talk about the topological insulators, and I'm going to start with the two-dimensional version of that, which is also known as a quantum spin Hall, so a 2D quantum spin Hall insulator. And the way I want to start off with that is sort of historically the way the sort of idea materialized, at least for me, which was by thinking about graphene. Again, graphene as a model system as opposed to being an actual system. Okay, and so let me remind you that so let's think about the energy gaps that we had in graphene. Because remember, graphene has these Dirac points, and a point that I want to make, and I'm going to make it over again, is that Dirac points are interesting, but one of the things that's most interesting about them is the ways that you can kill them. Okay, and so in graphene we have this Dirac Hamiltonian, and let me write it in the following way. Okay, so what I've done here is I've just I've introduced a new Pauli matrix tau to account for the k and the k prime, the valley degree of freedom. So this is the valley, you know, at plus or minus k. So tau z is plus or minus 1 for the k or the k prime point. And so in particular, what we noticed, and v is going to be some perturbation. Okay, and which maybe lowers symmetries and opens a gap at this. So V is going to be something which involves sigma z, so that it opens a gap at the Dirac points. And so the first one that we thought about was you know, just a sort of trivial insulator. You know, for instance, boron nitride. If we have different atoms on the A and the B sublattice, then we just get a sigma z term, and that gives us a trivial insulator, and it breaks P. Okay, it breaks inversion symmetry. Okay, by having the different atoms on the A and the B sublattice.
You mean my sigma z and identity?
Pardon me? Yeah, that's right. Yeah. So it's that important. So the point I want to make is that the mass here is the same at the k and the k prime point. Okay, it has the same sign. Okay, whereas in Haldane's model, Haldane introduces a different kind of periodic perturbation. Instead of a electric field, if you will, he introduces a magnetic field that's periodic. And in that case, so if I have Haldane's mass term, that has opposite sign at the k and the k prime point. So I'll write that as a tau z mass term. Okay, and so this gives me a integer quantum Hall effect. Okay, but it breaks. It breaks T. Okay, so you break time reversal symmetry. Okay, and so back in when people were just starting to rethink about graphene because it had the potential for actually being a system instead of just a model system. So I asked the question, well, is this all there is to say? And if you think of the fact that actually electrons have spin, then one can conceive of a mass term that doesn't break any of these symmetries. Okay, and so I want to think about a intrinsic spin-orbit term. So let me write it as and so now S is a Pauli matrix for the actual spin of the electron, so for the upspin and for the downspin. Okay, and so what you can see from this is that Haldane breaks time reversal symmetry because tau z goes to minus tau z. K goes to minus k under time reversal, so tau z goes to minus tau z. But this spin also goes to minus spin under time reversal. Okay, and so this respects time reversal, and so this respects all symmetries. Okay, and so if you believe in the mantra that anything that is allowed by symmetry will be present, then you have to accept the fact that graphene will have an energy gap. Okay, because this term is allowed by symmetries, and if you look at all the crystal rotational and mirror and this respects every symmetry. Okay, and so it has to be there. Okay, the catch is that it involves an interaction between the spin and the orbital degrees of freedom. So this argument that everything that's allowed by symmetry must be present, that's a good thing because the good thing about it is it's right. Okay, but the bad thing about it is that it doesn't tell you how big the term will be. Okay, and the fact is that in graphene it's going to be puny because graphene is made out of carbon, which has a very weak spin-orbit interaction. Okay, but nonetheless, my approach to this was, rather than thinking of graphene as a system, I'm thinking of it as a model system, where actually this invites us to think what kind of phase of matter does this lead to. Okay, is it a insulator quantum Hall? And actually, it's something new. Okay, and so the way we can think about this.
So is there any simple way to see that output?
Yes. Yes. Yeah. So what one can do is one can. So I'm not going to go through this, but you can write down what the microscopic spin orbit interaction is. So the microscopic is going to be something like so you're going to have the spin of the electron. Let me call it S cross the momentum, dotted into the gradient of, dotted into the electric field, basically. Okay, and so this is something which you can, and then there's a coefficient here which depends on the mass of the electron, the speed of light. This is the sort of relativistic correction to the Schrodinger equation. Okay, and so then you can imagine trying to evaluate this. And so what we did at first was to just say, let's imagine we're doing some sort of k dot p approximation. So we have the wave functions at the Dirac point, and we can evaluate this term in those wave functions. Okay, and and just from symmetry, you know that the answer you get is going to be non-zero. Okay, now that's not a particularly accurate calculation of this. Actually calculating this accurately, you need to know the details of the wave function, sort of, and that's a hard thing. But as a matter of symmetry, you know that this is going to be non-zero. So basically, what you do is you do first order degenerate perturbation theory in this interaction, and what you find is that you generate this term. Okay, all right. Pardon? E is the electric field. So it's the gradient of the crystal potential, right? So, there's some potential that has, the, Coulomb potential of the atoms in it, and E is that electric field. And, the reason this is coming about is because, in heavy atoms, the electrons are sort of moving in this crystal potential. They're going around, and they're actually moving at a speed which is a not insignificant fraction of the speed of light. And so then the relativistic corrections become important, and that's the origin of the spin-orbit interaction.
Which component of E is NSO?
What's that?
Which component of E is NSO?
Which component of E?
Yeah, right. E has the price.
Well, it's a combination of E and P. I mean, yeah.
Yeah. What is the?
All of them. I mean, yeah, they're all. I mean, this is a scalar.
Well, the other one you've just written sigma Z.
Yeah. So okay, I see. So look, both P and E are in the XY plane. So S is going to be in the Z direction. Yeah. So it's the X and Y components, if you will. Yeah. Okay.
What sort of magnitude does it have in graphing? What size splitting does it make?
Yeah, it's small, and so and people have argued about whether it's really small or really small. And so the numbers, I think it's a question of whether it's microvolts or maybe tens of or hundreds of microvolts, something like that. So the question is whether it's Kelvin or millikelvin. Do you remember those numbers? Yeah. What's that? It may so that has yet to be measured. Okay, so yeah. So, but I think the point of view that I want to take here is rather than actually thinking that we're trying to describe graphene. Okay, I want to be thinking of graphene here as a model system where it's really a nice it's a simple context in which we can understand the physics of this new phase, and then we have to recognize that the smart way to go about finding this physics is to finding it in materials that actually have a stronger spin-orbit interaction. Okay, so what does this do? So really what this mass term is, notice that SZ is still kind of a good quantum number. And so really this just gives me two copies of the quantum Hall effect. So I can write it as Haldane squared. Okay, so I have a Hamiltonian, which if I write it for the up and down spins, it's going to be Hamiltonian for the up spins and Hamiltonian for the down spins. Okay, and what this is just the Haldane model for the up spins with sigma xy equals +1, say, and then the Haldane model for the down spins is just the time reverse of that. So it'll just look like that. And so once you have that, then you immediately know what's going on. Okay, so in particular, you have an energy gap in the bulk, but Haldane model describes a quantum Hall state. So that means, for instance, that if you apply an electric field, you get a Hall current. So that means that when you apply an electric field, the up spins go up, the down spins go down. Okay, so there's no net current that flows. The Hall sigma xy is equal to 0 because the up and down spins cancel each other out. But there's a sense in which there's a spin current. Okay, now the spin current, of course, one has to be a little bit careful with when one thinks about spin current, because when you have a spin-orbit interaction, spin isn't really conserved. But certainly in this picture, SZ is conserved in this simple picture. And in that case, there really is a spin current. There's a net flow of up spins going up and down spins going down. So there's a sense that there's a flow of SZ going up. Okay, so that's why we called it the quantum spin Hall effect. Okay, because there's a sense that an electric field induces a spin current. Okay, but one has to be careful with when we're talking about spin currents when you have a spin-orbit interaction. So, but a more important consequence is the fact that this has edge states. Okay, because we know that the quantum Hall effect has edge states. So so if we have a system where we have the quantum spin Hall insulator and we have a boundary, then there are going to be, the upspins are going to have an edge state which, say, goes this way. So this is the upspins, okay? And the downspins are going to go the other way. Okay, and so this is it's kind of a different kind of edge state in the sense that it's not chiral anymore. There are things going in both directions. Okay, but somehow there's a difference between the left and right movers. They have different spin. Okay, and so if you were to make a plot of the band structure of this, so if I was going to draw the energy as a function of k, so let's imagine we have a strip. Okay, so I can do it as a function of k in the x direction here, and so I'm going to draw it again in the Brillouin zone, and so this basically so there's going to be so we have an energy gap, and so there's sort of the projection of the k point and the minus k point. I'm imagining I have a sort of zigzag edge of my graphene, so that if I look at it, I see the projection of the k point and the minus k point, and so there's going to be these are the sort of bulk states that live in the interior of your sample, but they have an energy gap. But then there's going to be the edge states, and the story is the same in the Haldane model. In the Haldane model, what we would have seen is that the upspins get an edge state that sort of looks like this. Okay, so this is, if I just had the quantum Hall effect, if I just had a single copy of Haldane's model, then I'd have an edge state that goes like this, and this state is localized right here. Okay, and that's the edge state. Now, of course, in this quantum spin Hall, then we have the downspins as well, and so they're going to be like that. And well, I didn't draw this very well. I'm going to move the middle. There, that's better. Okay, okay, so this is the downspins, and these are the upspins. Okay, so when I first realized this, I thought, oh, this is nice. Okay, but there's something about this which is disturbing, which is that the chiral edge states are wonderful because it's impossible to get rid of them. Okay, there's nothing you can do if you just have a single chiral mode. There's no perturbation you can add that can do anything to get rid of it. Whereas now, when we have these crossing edge states, they're degenerate here. Okay, and one of the first things you learn when you study quantum mechanics is that degeneracies don't happen by accident. Okay, because if you have a degeneracy, you can always add a little perturbation, and generically, to first order, that degeneracy will be split. Okay, unless there's a good reason for that perturbation to be zero. Okay, and so here, of course, in this model, it's kind of trivial. It's because we have the up and the downspins are independent of each other, and so that allows them to cross. And so the first thing you might think is that, well, this is an artifact of the conservation of SZ. Okay, and if that's the case, then you might think, well, if I just put some perturbation that violates the conservation of SZ, after all, we're talking about a spin-orbit interaction, so spin no longer has any reason to be independently conserved, then that should get rid of this. Okay, and so I typed it into my computer, and I started adding terms that violate SZ conservation, and I couldn't couldn't get rid of this degeneracy, no matter how hard I tried. And so that was a hint that there's something more interesting going on there. Okay, and the thing that's more interesting that's going on is time reversal symmetry. And so I want to say a word about time reversal symmetry. Okay, so time reversal symmetry is a symmetry of the Schrodinger equation, but it's a little bit of an unusual symmetry. It's not like rotational symmetry or translational symmetry, which are described by having a Hamiltonian commute with a unitary, operator. Instead, the time reversal does two things. So if I have a wave function, I have a time reversal. So it's still an operator that commutes with the Hamiltonian, but this operator is an anti-unitary operator. Okay, so it does two things. I'm sorry. It does two things. One thing is it rotates the spin. It sort of takes the up spins to the down spins. That's what this pi rotation about SY does. And but it also takes the complex conjugate. Okay, so this is what time reversal symmetry, how time reversal symmetry is represented in the Schrodinger equation. Okay, now so in particular, if I have a spin a half particle, what this means is that if I do time reversal on a on a spin a half particle that has an up and a down spin component, then it interchanges the up and the down spins with the complex conjugate. But it also does another important thing, which there's this minus sign here. Okay, and that minus sign comes again from this pi rotation about the y-axis, and this minus sign is it's actually the same minus sign as the minus sign that you get when you rotate a particle by 2 pi. Okay, when a spin a half gets rotated by 2 pi, you pick up a minus sign. It's the same minus sign showing up here. Okay, my favorite. And so this minus sign has the consequence that if you do this twice, it squares to -1. Okay, and so this -1 has a consequence which at first sight seems trivial and simple, which is Kramers' theorem. Okay, and so Kramers' theorem says that for spin a half, all states are at least twofold degenerate. Okay, if you have time reversal symmetry. Now, of course, if you don't have a spin-orbit interaction, it's completely trivial, right? It's just that, in every orbital, you can put an upspin particle or a downspin particle, and those two have the same energy. Okay, so that doesn't seem so interesting, but when you have a spin-orbit interaction, and you can't independently talk about the spin and orbital degrees of freedom, then it has more content. Okay, and so in particular, let me just show you why this is true. So let me prove this for you. And I'm going to prove it by assuming that it wasn't true and then showing there's a contradiction. So let's suppose that we have a spin a half particle and let's suppose it was non-degenerate. So let's suppose we have a state chi that's non-degenerate. Then we know that if the Hamiltonian commutes with, if this is an eigenstate of the Hamiltonian, then we know that the time reverse on it has to give us the state back up to some constant, like that. Okay? If we do that again, then what we're going to get, so since time reversal is anti-unitary, when it goes through C, it turns it into C star. Okay? And then we have to operate on chi, which then gives us just C chi, like that. Okay? And so that tells us that theta squared, basically acting on this state, is the magnitude squared of C squared, and there's no way that can be equal to -1. Okay, so that's a contradiction. Okay, so when you have time reversal symmetry, you always have a twofold degeneracy. Okay. But I don't care. So when you have time reversal symmetry, you never have non-degenerate states. Okay. And so now we can look over here and sort of realize that what's going on here is something very interesting. Okay? Because now, of course, under time reversal symmetry, k goes to minus k. Okay, so in most of the places here, it's perfectly okay for this state to be non-degenerate. Okay, k goes to minus k, but at 0, this state has to be twofold degenerate. Okay, so this crossing here is protected by time reversal symmetry. Okay, and so that was the reason I couldn't get rid of it, is because I was adding time reversal symmetric perturbations. They violated SZ, but they kept time reversal. Okay, and so this Kramers partner, these Kramers partners are never lifted by any time reversal invariant perturbation. Okay, and so that suggests that time reversal symmetry protects these edge states.
So what is the corresponding picture on the armchair edge?
What's that?
What's the corresponding picture on the armchair edge?
On the armchair edge, then when you're looking on an armchair edge, then the k and the k prime point sort of project on top of each other, so you get something that you just have a single gap that looks like this, and in that case, you'd have something that looks like that. Yeah. Good. Okay. So time reversal really protects these, and so you can actually so let's just think about how well time reversal protects these states. Okay, so certainly it protects this crossing, but so now we have this sort of one-dimensional metal on the boundary of our system. Okay, now the first thing you think when you have a one-dimensional metal is that it should be unstable in the presence of disorder. Okay, and actually that's the wonderful thing about the quantum Hall effect, is that the quantum Hall effect is immune to disorder. Okay, so you might think that, well, let's suppose we add impurities, which will inevitably be there in any real system, to this. What could happen? And so the first thing you can think is that the first thing you do is you say, well, if I do perturbatively, then the impurities maybe could lead to some elastic backscattering. Okay, but actually, if you think about it, elastic backscattering necessarily involves a spin flip, and so that is accomplished by the operator S minus, right? Sx minus Isy. That's the operator that takes an upspin to a downspin. That operator is odd under time reversal symmetry. So that cannot appear in the Hamiltonian. Okay, and so elastic backscattering is forbidden. Yeah, but yeah, okay, fine. Okay, so I'm going to give you a better argument. So this is I'm sort of so it's a fact that even if I turn on the spin-orbit interaction, the operator that takes me from the left moving state to the right moving state necessarily is odd under time reversal. Okay, that's the that, and you can see it. It's obvious in the case when if I imagine starting from this decoupled up and down spin. Okay. So so elastic backscattering is forbidden. Okay, and basically, I'm not going to give you the proof of that, but basically, the way you know this is the states that you're scattering between. You have these two states that you're scattering. You're scattering from here to here. They're at the same energy. Those two states are Kramers partners. Okay, and any operator that mixes the Kramers partners must be odd under time reversal symmetry. Right, because otherwise it would violate Kramers' theorem. Any operator that would mix these two states would split them, and that's what Kramers' theorem prevents. Okay, so elastic backscattering is forbidden. Actually, I can make an even stronger statement than that, which is that all states are extended even for strong disorder. Okay, and so let me give you the argument. So let's imagine that I have an edge, and I'm going to imagine that I have, the edge is infinitely long, and I have and inside that edge I have an arbitrarily long disordered region. Okay, but I'm gonna allow myself to say that outside that disordered region I have it's clean, so I can talk about these edge states. So I have a disordered region, and then I have outside the disordered region, I have my pristine edge states. Okay, and so now I want to ask the question. Let's suppose I'm an electron, and I'm coming in. I'm coming in from the left, so I have some psi in here coming in. What happens to me? Okay, well, so I know I have a gap down in the bulk. I'm assuming I have a gap in the bulk. So I'm assuming that the disorder is not so great that I have destroyed the gap in the bulk. Okay. So what could happen? Well, there are really only two choices. Either I could be reflected, and there will be some amplitude r for reflection, or I could be transmitted, and there will be some amplitude t for transmission. It's just a simple transmission problem, just like in first-year quantum mechanics. Okay, something that has a transmission and a reflection amplitude. Okay, now so the thing that you can check. So if you think about this reflection amplitude, notice what you're doing is you're coming in on a state and you're coming out in the Kramers partner of that state. Okay? And so it's an exercise to convince yourself that the fact that these two are Kramers partners of each other implies that under time reversal symmetry, R is odd. Okay, so under time reversal, R goes to minus R, which means that if you have time reversal symmetry, R equals 0, so T has to be equal to 1. Okay, so that means it's impossible to have localized states. It's impossible for the states to be localized in here because any electron that comes in, no matter how long this and how strong the disorder is, it has to be able to come out the other side. Okay, so these edge states evade Anderson localization, which occurs in any ordinary disordered one-dimensional conductor. Okay, so in that sense, like the quantum Hall effect, they're special. Okay, they're protected in a sense. Okay, it's not quite as good as the quantum Hall effect because, of course, if you allow yourself to break time reversal symmetry, then in principle this all goes away, and the states can become localized. Okay. I'm only talking about elastic. That's a very good point. Okay, so I'm talking about zero temperature. The eigenstates of the system. Okay, now at finite temperature, then maybe you can scatter off of phonons, or there are processes. Maybe you could do a backscattering, kicking up a particle hole pair. Okay, so there are inelastic processes that can occur. Those processes are not forbidden. Okay, so because for those processes, so the thing is, when I do the reflection, if I think of it as a motion picture and run the motion picture backwards, it looks exactly the same, right? So if I come in and I'm reflected, if I run it backwards, then I'm doing the same thing. Okay, but if you have an inelastic process, it doesn't look the same because if you're having a process where you're reflected and emitting a phonon, when I run it backwards, I'm absorbing a phonon instead of emitting a phonon. So those two processes are not the same, and for that reason, time reversal symmetry does not forbid inelastic scattering. So in general, if you have inelastic backscattering processes off of phonons or other electrons, then those can lead to reflection. Okay, and those in general will lead to a finite conductivity of your edge. Okay, and so that's a sense in which these edge states are less protected than in the quantum Hall effect, where even for inelastic processes, there's nowhere for the electrons to go but forward. Okay.
But then I introduce disorder to introduce the top. If I have two.
You mean the other edge? Of course. Oh, of course. I'm assuming. I mean, that's the same thing is true in the quantum Hall effect. Okay, if you don't have the, so we're relying on the fact that the bulk has a gap, and that so there's an exponential decay into the bulk, and your width is much larger than that exponential decay. If that's not the case, then of course you can always then it turns into just a regular one-dimensional system, which gets Anderson localized. And that's true in the quantum Hall effect as well. Yeah, exactly. Yeah, that's right. Yeah. So then there's another copy of this on the other side. Yes.
Is there anything that we can talk about rate of T?
That'll depend on what's going on in here. So in general, there can be a forward scattering phase shift. That's okay. And that could be anything. Okay. All right. So what we see here is that there's something special about these edges. They're protected. You can't get rid of them. It's impossible to get rid of them. And so you can ask the question, well, what is it about the bulk, the interior of this quantum spin Hall insulator, that knows that it has to have an edge state? So there must be some structure, some bulk structure. Remember, in the quantum Hall effect, in the bulk, we had the Chern number, which topologically characterized the bulk. And if the Chern number was non-zero, you have to have the edge states. Okay? So what do we have here? So now, of course, we have time reversal symmetry, which means that the Chern number has to be equal to 0. Okay, so that's not the Chern number. So there must be something else. Okay, and so in fact, what we now know is that for Hamiltonians, so if we constrain the Hamiltonians such that they such that under time reversal, h of minus k is the time reverse of h of k. Okay? So if we add this constraint to the topological classification problem, so now I'm only classifying Hamiltonians that satisfy this constraint, then what we get is that there is a Z2 topological invariant. And what that means is that there are two classes of time reversal invariant two-dimensional insulators. One of them is trivial and doesn't have to have edge states. The other one has these edge states like I showed you. Okay? And so so it was a hard problem to figure out this Z2 invariant. Okay? That was hard for me. But a simple thing that one can see is that there are two and only two possibilities. And so let me first convince you of that, and then I'll try to construct for you what this Z2 invariant is. No, it's something. It's a little bit harder. And I'm gonna argue this by again thinking about the edge states. Okay, and so what I'm going to do is I'm going to draw this picture again, but I'm going to draw it a little bit more schematically. I'm only going to draw half of it, actually, because you know if you have time reversal symmetry, this half is related to this half. So I'm going to make a plot. So I have k equals 0, k equals pi. Okay? And so again, in general, I'm going to have some bulk states that are separated by an energy gap. Okay? And now, you can always, if you have a gap and you have surface states, you can always have states that are localized on the surface. The surface states are always possible no matter what. Okay? The thing you know, though, is that at k equals 0, if you have a surface state, it has to have a partner. Okay, so it has to be doubly degenerate. And as you move away from k equals 0, in general, if you have a spin-orbit interaction, of course, if you don't have a spin-orbit interaction, then every state is twofold degenerate. But if you have a spin-orbit interaction, then in general it'll split because, again, this guy's partner is at minus k. Okay? Now, so this is true at k equals 0. Now, remember, k equals pi is the same point as k equals minus pi. So that means that at k equals pi, you also have to have Kramers partners. Okay? And so the interesting question is, how do these Kramers partners connect up with these Kramers partners? So one possibility is sort of the trivial possibility, is that they sort of connect like this, and maybe this one goes up. Okay? And if it looks like this, then these are not protected because I can just take these and imagine deforming my Hamiltonian, taking these, pulling these down, and pushing these up and getting rid of them completely. So these edge states are not protected. They don't have to be there. They could be there, but they don't have to. And so, so this is a conventional insulator. Okay? But when you think about it like this, you can immediately see that there's one other possibility, okay, which is that your Kramers partners could switch partners. So instead, they could connect like that. Okay? And if they connect like this, then you can see that you could pull these up and down all you want. You can't get rid of them. You can't get rid of them as long as you keep time reversal symmetry, which glues these states together at these time reversal invariant points. This is k equals 0. K equals pi. Okay? And so this is the topological insulator. So this one I'll call nu equals 0, nu equals 1, where nu is my Z2 topological invariant. Okay? Yeah? Yeah, so this you could say is exactly. I don't. I'm saying there could be. I mean, of course, I could pull this. I could imagine deforming it and pulling it down, and I could deform and pull that one up, and then it would look like that. Okay? Or I could pull. There could be more of them, but the thing is that the pattern is that it has to go zigzag, zigzag. You know, the valence band and the conduction band have to be connected by these surface states. You can't get rid of them. Okay. You know, but you know, it doesn't tell you how. And you know, the other thing, it could also, you know, maybe they could do that too. And so there might be lots of states at the Fermi energy. Okay. So you can ask yourself, what's the difference between this and this? So there might be states at the Fermi energy here also. But here you can see that there's always going to be an even number of crossings. Okay? And here you can see there's always going to be an odd number of crossings. Okay? And so the difference between the edge states here and here is you have an even or an odd number of crossings. Of course, the even number might not be 0. You might have surface states or edge states. But the odd number cannot be equal to 0. Okay? All right. Okay. So hopefully this convinces you that there are these two different phases, which are kind of like the different phases in the quantum Hall effect, where there we have an integer, you know, class of different numbers of phases characterized by different integers. And again, before I sort of try to calculate this Z2 invariant, I want to try to understand physically how we can think about what the difference between these two states is. And so what I'd like to give you is some kind of a variant on the Laughlin argument. Okay, and so remember, Laughlin's argument was this very nice argument where you put the quantum Hall state on a cylinder, and then you discover that when you thread a magnetic flux through the cylinder, you do something drastic. You pump an electric charge from one end of the cylinder to the other. So I want to think about a similar kind of construction for the quantum spin Hall insulator to try to characterize the difference between a trivial insulator and a topological insulator. So I want to give you a variant on the Laughlin argument. So I want to consider my cylinder. And I'm going to thread magnetic flux. Okay. What I'm going to do is, now remember, for what Laughlin did is he threaded a whole flux quantum. What I'm going to do is I'm going to thread half a flux quantum. So I'm not going through a complete cycle. I mean, I'm not coming back to exactly where I started. But the thing that's significant about half a flux quantum is that when the magnetic flux going through here is equal to 0, then I have time reversal. You know, the magnetic flux breaks time reversal in general. But when the flux is 0, I have time reversal symmetry. When the flux is half of a flux quantum, well, half a flux quantum is gauge equivalent to minus half a flux quantum, and that's what time reversal does. Okay? So when you have half of a flux quantum, then your system has time reversal symmetry. It's kind of the same as, under time reversal, k equals pi has time reversal symmetry, right? Because pi and minus pi are actually the same point. Okay? So that means that there's a special significance. And so what that means is that when the flux is either equal to 0 or pi over 2, phi naught over 2, you have Kramers' theorem that says that states have to be degenerate or not. Okay? So let's think about what's going to happen. So if I thread this half of a flux quantum, then so let's think about what happens in the simple case where it's really just two copies of the Haldane model. Just two quantum Hall effects for upspins and downspins. Okay, so then it's just like Laughlin's argument. I thread the flux, I'm going to pump some charge, but since I'm only pumping half of a flux quantum, then that means that the upspins I'm going to get 1/2 of a upspin gets pumped to the right, and half of a downspin is going to get pumped to the left. Okay, so there's no charge that gets pumped across. Okay, but at the end of the day, what I get is SZ goes to SZ plus 1/2. So it's as if I get an extra spin 1/2 at this end and an extra spin minus 1/2 at this end. Okay, so it's like I've changed the total spin at the end by h bar over 2. Okay, now the thing what Kramers' theorem says is that when you have a integer spin, the states aren't degenerate, but when you have a half integer spin, the states are Kramers degenerate. And so if I look at the many body spectrum now, so I'm going to draw a plot of the energy, and this is the many body spectrum. Okay, as a function of flux. So I have 0 and phi naught over 2. Then what happens here is I start off, and so let's suppose I start off in a situation where all of my states are, where all of my Kramers pairs of states are all doubly occupied. So the ground state then has an even number, of electrons, and so I start off with a spectrum that looks like this with a unique ground state. When I've gotten to phi naught over 2, then I have to have a doubly degenerate ground state. Okay, and so here I have a Kramers degeneracy, and here I have no Kramers. Pardon? Okay, so the argument is that when I thread half of a flux quantum, it's as if I change the spin at the end by 1/2. So that means that the states at the end go from, so it's as if I added an electron to the end. It's kind of like changing the polarization. Okay, so it's as if I add an electron. It's as if I change the number of electrons at the end from being even to being odd. Okay? And so that means that whether or not you have a Kramers degeneracy in the many-body ground state changes from either yes to no or from no to yes. Okay? And so in the way I drew it, it goes from no, it's like I have an integer number of electrons to having a half-integer number of electrons. Okay? So the process of threading half a flux, it doesn't transport any charge, but it transports the whether the charge is even or odd, the parity of the number of electrons. Okay? And that is reflected in a concrete way by the existence or non-existence of a Kramers degeneracy in the many-particle spectrum. Yeah?
That's the many-particle spectrum of the edge, or?
Good. Yeah. So I'm looking. Yeah. So of course the total system will also have the other edge, and so there will be another set of states that are on top of that as well. Okay. But things are sort of since I have a gap in the bulk, it makes sense to focus on what's going on at one end. What? Yeah. Yeah, I'm not coming back to myself. Yeah. But you see, the thing is that something has changed when I thread half of a flux quantum. Okay? And something sharp has changed. And it's that sharp change which is the essence of this Z2 invariant. And the sharp thing that has changed, you see, if you have a trivial insulator, then nothing knows about this magnetic flux because everything's kind of localized. And so nothing happens when you thread half a flux. Okay? But if you have a topological insulator, then you have this change of the local fermion parity. Okay? And so one has to think about how one defines a local fermion parity. I don't want to get too much into that, but I think on physical terms, it kind of makes sense. And certainly, if you think in the non-interacting picture, this is exactly what happens. Okay. So if you ask what happens if you have edge states like this, and you thread the half of flux quantum, you see you do exactly this switching. Okay. Well, I used that in order to motivate the fact that it's sort of like changing the spin by a half. I was just trying to motivate. So certainly in that case, SZ at the end does change by 1/2. Okay? Which implies that the local Kramers degeneracy changes. Okay? Now, of course, if I relax the conservation of SZ, I can't talk about SZ anymore, but I can still talk about the local Kramers degeneracy. That remains well defined even when I have a spin-orbit interaction. Okay? Yeah. I'm sorry. Could you start that again? I couldn't hear it. Louder. Well, if I had a conventional insulator, then everything. Nothing happens when you thread the flux. Okay, and so in that case, you'd have a picture which basically looks like this, right? So you have some ground state, and you still have a ground state when you and it's still unique when you after you've threaded the flux. Well, no, there's no channel here either. There's no edge state that is running along the cylinder. It's not. This is happening in the bulk. There's a gap everywhere here. So it's really a property of the bulk, not of some edge channel. Yeah.
So I can see the argument of transferring the path dead.
Well, I'm using that, but I'm realizing that when I use that, I discover something that's more general than the SZ conservation assumption.
You are using it as a first step.
I'm just using that to motivate. Yeah. Okay. Okay. So yeah. Pardon? Well, because Laughlin's argument shows that the charge that gets pumped is exactly the flux in units of flux quanta. No, I don't think so. I think. What do you mean, integrating over the entire Brillouin zone? Well, no, but Laughlin, of course, is going through an entire cycle. Right. Yeah. Well, look, I mean, if I thread half a flux quantum, I transport half as much charge as I would if I threaded one flux quantum. And if I thread one flux quantum, I get a sharp E. So if I thread half, I get a sharp half E. So it's not that much more complicated. Yeah. But no, look, but that's not what I'm talking about, okay? So I'm just trying to motivate in the simplest terms having, this setup. So I'm going to move on. So the next question, okay? So I hope you can believe there's a difference between these two, between having, having this and not having this. And so the question that you can ask then is that what property of the bulk gives you that? Okay? And so again, so how can we describe this Z2 topological invariant? And so I thought I'm going to give you a little bit of a. There are several formulations of how you compute this Z2 invariant. And again, for me, this was a hard problem. And the first way I thought about it was not the best way. Okay, so it's not as simple as just integrating the Berry curvature over the Brillouin zone, which is the way we got the Brillouin zone. Okay, the way we got the Chern number. So I'm going to give you a formulation which has some conceptual value. Okay, and so the starting point is I have block wave functions. So let's suppose I have my block wave functions, which have and there are maybe n occupied bands in the valence band. Okay. Now, so I'm going to take as given that I can choose these block wave functions and define them continuously everywhere in the Brillouin zone. Okay, and that I can do because the obstruction to doing that is the Chern number, which is equal to 0. Okay, so given the fact that these are defined, then I'm going to come up with a very simple formulation for the Z2 invariant. Okay, now if you're going to do this numerically, okay, then the fact that this continuous gauge is guaranteed to exist is numerically it's non-trivial, because when you do it on a computer, you diagonalize your Hamiltonian for every value of k, your computer gives you some eigenvector, and it's not guaranteed to be continuous. Okay, and so if you're actually going to compute the Z2 invariant on a computer, you have to do some work in order to establish a continuous gauge, and there are various algorithms for sort of getting that right. Okay, but just conceptually, let's imagine that we accept that we have a globally defined gauge for our states. Okay, so then yes.
When you say n bands are occupied, you mean with both spins, so that for each state the time.
Well, I have spin orbit interaction, so everything spin is mixed. So
language you want to use, but for each occupied state, time reversal part also occupied.
Yeah, of course, because I have time reversal symmetry. I mean, the time reverse, but the time reverse is at the state at k is at minus k.
Yeah, but it's not necessarily the case that they have.
Look, let me put it this way: the number of bands is even.
Okay, that's what I'm asking.
Okay, it's guaranteed to be even.
Well, it's probably also important that it's even because they're all time reversal parts.
No, time reversal symmetry requires.
You still have bands that cross the Fermi energy and the.
No, I'm talking about an insulator, though. I don't have bands that cross the Fermi energy. Yeah. Yeah. Okay. All right. So. Okay. So what I want to define is an object which describes the relationship between the states at k and the states at minus k. Okay, so this is a matrix. This is an n by n matrix, okay, that compares the states at k with the time reverse of the states at minus k. Now, since I have time reversal symmetry, the states at k are the time reverse of the states at minus k. And so that means that this matrix, that the states at k are related to the time reverse of the states at minus k by a unitary transformation. So this is a unitary matrix. Okay? But this unitary matrix has a special property, which is that, since time reversal squares to minus 1, what I can do is I can if I have this overlap, I can make a new overlap, which is the overlap of theta squared on this with theta on this. And since theta squares to minus 1, what that implies is that W at k is equal to minus, and that's this minus sign, the transpose of W at minus k. Okay, so it's not too hard to, using the property of matrix elements of anti-unitary operators, it's straightforward to see this, and this minus sign is this minus sign. Okay? So what this means, in particular, is that if I look at, so here I have a Brillouin zone, kx, ky. If I look there are these 4 special points where, at 0, k is equal to minus 0 is equal to minus 0. Pi 0 is equal to minus pi 0. Pi is equal to minus pi. So these 4 points, k is equal to minus k. So in particular, this implies that for k equal one of these time reversal invariant points, W is a skew symmetric matrix. It's sort of anti-symmetric on the if I interchange the rows and columns.
How did you define your block functions?
How did I define the block functions to be continuous at those points? What's really important is the space that's spanned by block functions. So given my set of occupied block functions, I can choose any linear combination of those. Okay, and those will give me exactly the same many-body state. Okay, if I populate some linear combination of states, that gives me the same state. And so it's always possible to choose a linear combination of these states that span the same space, and those can be chosen continuously. I understand that you're worried about the fact that you have Kramers points and that it looks like something that it should be singular. But if I allow myself to choose linear combinations of the different states, then I can choose those linear combinations continuously. Yeah. Okay. Okay. So,
just another question that someone might ask at this point is whether the UN of K, as well as being continuous, come in a pair.
UN of K? What? Oh, well, certainly. So here's what I can say is that I have a set of states at minus K. Okay, and I have a set of states UN of K. The thing that I know is, and if I take the time reverse of these states, then what I know is that the space spanned by these states has to be exactly the same as the space spanned by these states. And these are going to be related by a unitary transformation. Okay, and in general, different gauges could have different unitary. I mean, how I choose the states at K and how I choose the states at minus K. I can independently make choices for what basis I use for those states. But there will always be a unitary matrix that relates them.
Can't choose them. Can't necessarily choose them. Maybe we'll anticipate.
Well, or I think you can choose it so that it is. You could choose it so that instead of being the identity, it's sort of 1 minus 1 on the off diagonal. That you could do, because time reversal has to square to minus 1, and so. But I don't think we need to worry about that.
You can't do that globally. You can do that locally.
What's that?
You can't pick 1 minus 1 globally. Pick 1 minus 1 locally.
So if you choose 1 minus 1, if you demand that you have this be equal to this 1 minus 1, then the Z2 invariant is the obstruction to choosing U continuously. Okay, so that's a different formulation of the invariant, which I'm not going to do. Okay, but one can do that as well. So I'm not making any. I'm going to imagine that W is. I'm not going to try to fix W. So, but what I can say is that at these special points, W is antisymmetric, and antisymmetric matrices have a very magical property, which is that they have a Pfaffian. So Nick told us about the Pfaffian yesterday, and the Pfaffian of a matrix has the property that the determinant of the matrix, the determinant of an antisymmetric matrix, is a perfect square. And it is the square of the Pfaffian. Okay, and so this is it's an amazing property of anti-symmetric, skew-symmetric matrices that they're determined as a perfect square. So I'm not going to prove that to you in general, but let's just think about the simplest one. If you look at the matrix, a 2x2 anti-symmetric matrix, the determinant of this is equal to z squared. So that's a perfect square, right? And so z is the Pfaffian of this matrix. Okay, and if you work it out for a 4x4 matrix, then you see that the determinant is again the perfect square of a polynomial in the entries of the matrix. Okay, and so what this fact means is that at these time reversal invariant points, we can define a quantity which I'm going to call delta of lambda A, which is equal to the Pfaffian which is defined, divided by the square root of the determinant. Okay, and so your first thought is that that's completely stupid, right? Because and so this has got to be equal to plus or minus 1. So your first thought, this is stupid because of course when I take the square root, I can choose whichever sign I want, and that'll change what sign I get. Okay, so this is completely ill-defined given the square root ambiguity of the square root. But notice that W is defined everywhere. So W is defined throughout the entire Brillouin zone, which means that I get to choose the branch of the square root once. And so that means that if I compare different time reversal invariant points, so if I look at delta of gamma A, delta of gamma B, and so this is going to be equal to plus or minus 1 as well. If I demand that I choose the same branch of the square root at both of those points, which is, and that's, W is globally defined, then this does not suffer from the square root ambiguity. Okay, but it's still problematic. So this, in fact, this fixes the square root ambiguity, but it's still not gauge invariant. In the sense that it's not gauge invariant in the same sense that the polarization was not gauge invariant. It is not gauge invariant under a large gauge transformation. So if I do the kind of gauge transformation that changed the polarization by an integer, then that will change the sign of this. So this is sort of like the analog of the polarization. Okay, so if I take the product of two of these, it's like the analog of the polarization. Okay, but like the polarization, so for the polarization, changes in the polarization were well defined, and that is what the Z2 invariant is. Huh? So if I do a large gauge transformation where the phase of my wave function wraps by, I change the phase of my wave function in a way that it wraps by 2 pi going around the Brillouin zone, then that will change. So let's suppose, I have the Brillouin zone is a torus going around this way, and so if I introduce a large gauge transformation which puts a 2 pi twist going around this way, then that changes this product to minus itself. Okay? But it also changes this product to minus itself. And so the product of the two of them is invariant. Okay? And it's really the same kind of thing happened with the polarization. So with the polarization, I had the Berry phase along this cycle, and that changed by an integer when I did this. But I also had the Berry phase along this cycle. That changes by the same integer. And so when I compare them, actually I guess I'm doing the Berry phase down here and up here. When I compare them, then it's invariant. Okay. All right.
I have a question.
Yeah.
Are we literally just computing the sign of the partition function at the K points?
No. Well, no. I mean, so it's important. You can't calculate this by just looking at one of the K points. Okay. So this is sort of hiding some subtlety here, right? So if I just had the Hamiltonian at these lambda a's, then I wouldn't know what sign to choose the square root of the determinant. Okay. So you have to do so this is really a global property. It's crucial that you choose this gauge which is defined continuously. So you're guaranteed that you can do that, but that requires global information. Yeah. Well, yeah. Okay. So in general, this is in general, it's not so easy to calculate this in general. It's easier if you have some extra symmetry. So for instance, if you have the spin conservation symmetry, then it's kind of easy. Okay, because then you can just calculate the Chern numbers for the up and the down spins independently. And then this then turns out to just be whether the Chern numbers are even or odd. Another way that it is simple is that with inversion symmetry, if I have inversion symmetry, then this delta at gamma A is equal just to the product of parity eigenvalues. So every state at these points, if you have inversion symmetry, is going to be either even or odd under parity. It's going to have an eigenvalue plus or minus 1. And so what one can show is that in that case, this Z2 invariant is just that this delta in a particular gauge is equal to just the product of the parity eigenvalues. Okay, so this makes it easy to compute the Z2 invariant. You just need to look up the parity eigenvalues and multiply them all together.
That's still having time reversal.
Yes, yeah, with P, of course, yeah. If you don't have time reversal, then we're not talking about topological insulators. Yeah.
For non-square lattice, are we guaranteed we always get even number of time reversal invariant?
Yes. Yes. Yeah. There's always, in 2 dimensions, there's always 4. Okay. All right. So I finish in 5 minutes, right? Okay. Well, I only have, an hour to go. But I will finish. So I guess I will. Let me just finish by talking about the real 2-dimensional topological insulators, and that'll have to be it. My notes go further. Okay, so so we thought about this in graphene at first, and that was really a model system. The smart way to make this come to life is to think about materials with a strong spin-orbit interaction, and so there, mercury cadmium telluride is the perfect system. And so this was an insight by Bernovig, Hughes, and Zhang. And also experiments by Molenkamp. A little bit later. And so the thing about mercury cadmium telluride, it's a semiconductor. Okay, it's a usual semiconductor. So cadmium telluride is actually kind of a conventional semiconductor in the sense that its band structure has the band structure that a usual semiconductor has. Okay, it's sort of like gallium arsenide. It has sort of S-like states in the conduction band and P-like states in the valence band. Okay, so mercury telluride, on the other hand, due to the fact that mercury is very heavy, okay, relativistic effects start becoming important, and what that has the effect of is moving the relative order of these bands, and essentially the S state sort of moves below the P state, and so it ends up having a structure that looks like this, okay, where the S state and the P state have become inverted. Okay, and so the notion of this band inversion, makes one think that maybe one can go through some kind of transition in doing that, and so that's the real insight that Xucheng Zhang sort of introduced to the problem of trying to engineer band inversions. Okay, and so in particular, if you have a quantum well structure, making in 2 dimensions, so you make a little sandwich where you have mercury telluride in the middle, and then you have so actually what they use is some alloy of mercury cadmium telluride. Okay, but basically this is sort of behaving more like the conventional insulator, and this is this inverted one. Then you have a 2-dimensional quantum well that has some thickness d. Okay, and so what one finds is that if d is less than some critical value, which I think is 6.3 nanometers, then basically what you get is a quantum well which is kind of like the trivial. It's so thin that you don't really know that much about the band inversion, and it looks like this. So you get a 2-dimensional band structure where you have again the S state and the P state are in the conduction band and the valence band, and now the symmetry is lowered, so really you really just have these states are just twofold degenerate due to spin. Okay, but when you have a wider quantum well, then what happens is that these states invert. So you get the S state downstairs and the P state upstairs, and so there's a inversion that occurs. And between these two, if we assume for the moment that mercury telluride has inversion symmetry, which is not true, but it's actually reasonable to think about it that way, then you can see that the S and P states cross, which means that the product of parity eigenvalues is going to switch. Okay, so in this case, the product of parity eigenvalues is equal to +1, and it's trivial. In this case, the product of parity eigenvalues is equal to -1, and it's a topological insulator. Okay, and so this insight of Bernovig, Hughes, and Zhang then sort of led to these experiments by Molenkamp. And let me just, I guess the last thing let me do is let me just write down the Bernovig, Hughes, Zhang model. how one can do this. And this sort of really sort of gets at this idea of getting to the quantum spin Hall state by a band inversion. And so so let me just write down the BHZ model, and then that'll have to be it. So basically, the BHZ model takes into account the that you have two orbitals that are here, the sort of an S-like state and a P-like state, and I'm going to index those by tau z, and then they get coupled to each other by a spin-orbit type interaction. Where this is spin now, okay, and so in this case, if you have the so if the mass is bigger than 0, this is the uninverted case, and if the mass is less than 0, then it's the inverted case. Okay. Now, of course, this is sort of a low energy theory that is defined in the vicinity of the point where the inversion takes place. So this model by itself, of course, doesn't know which phase is the topological insulator and which phase is the trivial insulator. Okay, but we know that this phase is the trivial insulator. Okay, and so we know that the small d is the trivial insulator, and so that allows us to identify which phase is which. And so with this model, one can do the same kind of analysis that we did for the quantum Hall effect. You have domain walls, and you get edge states, but these edge states are helical edge states. They have both the right and left movers, and so this is a simple way of seeing that. And I wish I could go on for longer. But I can't. So, what else can one talk about? One can talk about three-dimensional topological insulators. One can talk about the surface of three-dimensional topological insulators. One can talk about superconductivity. There's a lot to talk about, but there's only so much time. So, thank you. Yeah.
BHZ model is the effective model for the 2D electron gas between.
Yeah,
the two layers.
that's right.
And as we tune the thickness, the effective model changes.
That's right. So you can sort of think that changing the thickness is tuning this parameter m. Yeah. Yeah. So basically, the way I see the BHZ model is that there's a critical point where you go through this transition, and the BHZ model is sort of a model that sort of takes that as your starting point, and then is looking at perturbations about that. And m is the perturbation that takes you away from that. So it's really sort of, so this particular model is really in the spirit of K dot P perturbation. Now, of course, one can also write down, and BHZ did write down, a tight binding model, okay, where you build in the fact that so in the tight binding model you can design it so that you know which phase is which, okay. And then you can calculate the Z2 invariant. The simple way you can do it is by just doing the product of parity eigenvalues. Yeah.
So this varying this thickness, we only do that to see the phase transition. If you were to take like half what you get, half what you get,
Wait, half and half? Then it's not two-dimensional. I mean, you mean just the interface? Then no, I don't think. No. Now. So one problem with that is that mercury telluride by itself actually doesn't have a gap. Okay, so again, you have this band inversion. These states This is actually a fourfold degeneracy, and that fourfold degeneracy is protected by the crystal symmetry of mercury telluride. Okay, and so if you just had, bulk mercury telluride on the bottom, then it wouldn't. Then you'd have a three-dimensional something that's not an insulator. Okay. Now, of course, if you strain the mercury telluride, so you lower the symmetry, then you do open up a gap here, and in fact, that becomes a three-dimensional topological insulator. Okay.
Due to your Kramers degeneracy, the product of all the parity eigenvalues should always be 1.
Very good. Thank you. Yes. So, but the parity eigenvalues come in pairs. I mean, so every state is Kramers degenerate, but both Kramers partners have the same parity eigenvalue. So I'm only taking one of them for each pair.
The parity eigenvalues can only change by a change in the spatial origin.
Huh?
The parity eigenvalues, they can only change when you change the spatial origin.
What do you mean they can only change when I change this?
They're only variant.
I don't understand what you mean.
But same time, the polarization is variant.
Well, no, the only way that the product of parity eigenvalues can change is if I go through a transition where I take an S state from the valence band and trade it with a P state from the conduction band. So the only way the parity eigenvalues can change is if I go through a transition where the gap goes to 0.
I disagree with this. Because this
You're disagreeing with the fact that it can be negative?
no, this particular the product of parity eigenvalues equals.
And again, I'm only taking each Kramers pair one. This is only half of the states because they come in pairs.
Right. My claim is that the product can change the parity eigenvalues like
Right, okay, so you could change this. You might change this. That would be like choosing a different gauge. Yeah, I agree, this could change. But that will not change this.
it changes for different reasons.
No, but it doesn't matter which spatial origin you choose. I agree with you that choosing different spatial origins could give you different plus and minus signs for the C's. Okay, and then maybe your deltas would be different. But I don't assign physical meaning to this delta by itself. It's only the product of all four that I want to associate with the topological invariant. Okay, so and that I guarantee you will be independent of which origin you choose for your inversion centers. Yeah. Yeah. Yeah, that's right. Yeah. Yeah. That, and the reason for that is because it's possible to backscatter into a state that is not the Kramers partner of the state that you started from. Okay? So in a real one-dimensional wire, you have upspins and downspins. And so, of course, you could backscatter into the Kramers partner. In fact, you won't. But you could also backscatter into the one that isn't your Kramers partner.
And that causes.
Yes. Yeah. Okay, let's take a break. Hey.
So I understand that in the physical alternative degree, Aldegger error cannot be exist because time reversal, but such term can definitely exist with an extra derivative. I mean, such binomial can exist, and I just want to mention that.